Okay, thank you very much, and thanks to Simon and the whole committee for inviting me. This is a very new area for me. This is the very first paper I've done in this area, and I obviously have a lot to learn, and I'm learning it as the conference goes along. With that, I should also emphasize that this is very ongoing work and joint work with a Knight of the Realm. He was knighted in the Queen's Honours List this New Year's Day. So, Sir Timothy, congratulations. Let me begin by mentioning just a few of the prominent issues that we've seen emerging from research on climate change. And of course, I've selected the ones that are going to be part of our paper. First of all, the general agreement, except in the White House and a few places like that, that greenhouse gas accumulation is driving global warming. There's a lot of uncertainty. You can't precisely predict what bad things will happen in what year. So you have to have kind of probability distributions about the damage in any particular year. And there's also general agreement that that's not a kind of standard normal curve, but fat-tailed with much bigger weight on possibility of large damages. What's more, the risk of these catastrophic events happening, it's generally agreed, will increase as greenhouse gases accumulate. This is a public bad for the whole globe, but the effects are not going to be uniform around the whole world. Some regions, some countries might, in fact, actually benefit. So issues of distribution of losses and disagreements among countries for that reason have to be taken into account. There are some people who believe that a technological solution will emerge, some kind of geoengineering that will make the whole problem go away, and any kind of conservation efforts that we undertake now might prove to be unnecessary. And so the problem has two-sided uncertainty. Either taking action right now might be wasting resources right now with no reward afterward, and inaction obviously will have risks of very bad things happening in the future. We want to construct a theoretical model that incorporates all of these things. We find numerical solutions for kind of plausible values of the underlying parameters. If anything, we take assumptions that are somewhat on the climate optimistic side. So the kind of numbers we get should be seen as lower bounds on possibilities of damage and what we should be willing to do to mitigate the damage. We'll use the model to evaluate and compare alternative policies. A very important part for us is to keep the model really, really simple. So it's solved using a very simple Excel file, and we'll make the Excel file available to anybody who wants it. You can just request it. So you can play around with it yourself, varying our assumptions as you like, and tell us in what ways your results differ, and we can have a useful dialogue. Again, I want to emphasize that this is very preliminary, very suggestive, exploratory work. But we find two kinds of things. One is that pretty substantial, and by that I mean somewhere between 1% and 5% for the ranges of parameters we look at, of GDP, we should be willing to spend to reduce the risks of these catastrophic events to the extent that I'll mention. And that happens even with fairly climate optimistic assumptions. And think that with US GDP of around $19 trillion, 1% of it is $190 billion a year, very substantial, and 5% is something that nobody I've seen mention as likely expenditure that might be justified. We also find that policies in different regions of the world, and therefore presumably in different countries, are going to be strategic complements that say what one country would be willing to spend would be an increasing function of what the other countries are spending. Upward sloping reaction curves in game theoretic terms. And that kind of fits in with some of the ideas of coordination games and so on that have come up in some of the other papers. So what are the kind of highlighted features of the model? First of all, we take the idea of fat tails to its limit by supposing that the catastrophic event is a Poisson process, which is really all tail. Either nothing will happen, or with certain probability, just one really bad thing will happen. And the arrival rate of the Poisson process, the probability of the bad thing happening in one period, is going to be an increasing function of the stock of greenhouse gas accumulation. So that captures the idea that the risks increase as these accumulations increase. We allow for the possibility of a geoengineering type solution by positing another Poisson process, such that if that event of the other process happens, the whole problem will disappear. There'll be no catastrophes afterward, and everything will proceed in the standard kind of things that happen in ordinary growth models. The simplicity idea, most importantly, we do not even try to characterize optimal policies. And that's for two reasons. One is that to find optimal policies, you need to know the whole cost function of mitigating risks to this extent, this extent, this extent, etc. And your finding will be very sensitive to the rate of increase and the convexity of the cost function you stipulate. And nobody that we read has a really good idea of what that cost function is going to look like. Secondly, as a matter of reality, nobody is really in international negotiations, for example, is seriously talking about optimal policies. They're merely talking about particular policies and what the willingness to sacrifice for them might be. And so what we do is exactly that. We find the willingness to pay, in economics jargon, the compensating variation for various policies. The paper has a slightly more sophisticated model in which the level of the damage, if the Poisson process happens, itself is a function of the greenhouse gas stock, et cetera, But I'm going to, for sake of this presentation, going to take a much simpler model. So let me begin to present that. First of all, little bit on carbon dynamics. The sense we get is that people believe that a part of carbon will stay in the atmosphere forever. That's the fraction epsilon, which is believed to be around 50% of what doesn't kind of instantly dissipate. Of the remaining, that's a non-permanent part, it will be roughly exponentially depreciating with a half-life of maybe like close to 25, 30 years, so depreciation rate of around 2.8%. And then you can put this through a standard, very simple mathematical formula, a permanent stock, a depreciating stock, and the state variable that we use will be the log of the total stock. The arrival rate of the catastrophic damage process will be a function of this state variable, and it will be a pretty standard sigmoidal function. We assume that the arrival rate of this miracle technology is just a constant. There are kind of arguments either way, and so this seemed a very simple start. Let me begin very roughly specifying our model of a unified world, or think of it as one region, under status quo policies. And the idea is that the GDP would keep on growing at a certain rate, G, and the discounted present value of the catastrophic process, if it occurs, K, will also be growing at the same rate, G. The flow of emissions will keep on growing at rate alpha. In the baseline parameter, we'll take alpha equal to G, and we'll examine the consequences of lowering that alpha by, for example, 30% as a kind of representation of the Kyoto idea. Everything will be discounted at a rate R, which is greater than G, mathematically for conversions, realistically, if you like, because Piketty tells us so. And with all of this, you can very easily calculate the expected net present value of the economy, the discounted present value of GDP flows, minus the cost of the catastrophe by doing a dynamic programming like recursion. And I want to say like because we are not doing any optimization. This is simply putting in next period continuation value, and then the continuation value will be similarly the following period's flow, and the continuation value beyond that, and so on and so on, and so you get sum. The first part of that is simply the discounted present value of GDP if nothing happens by way of catastrophes, and then a discounted present value of the catastrophes, which involves the catastrophic process probability, miracle process probability, and the other parameters. With many regions, the carbon is worldwide. So the parameters epsilon and delta are worldwide, and so is the state variable x. All the other parameters can, in principle, differ across regions. So even though the stock is worldwide, the probability of catastrophe happening in Bangladesh might be very different from the probability of catastrophe happening in Canada. What are the values of the baseline? Actually, no, there's a little bit more. We take baseline values of the parameters and change them, alpha, mu, et cetera, et cetera. And the nice thing is that the effects of all of those are channeled through this lambda. So if good policies are followed, lambda will go down, and the value of the economy will go up. And then we'll ask, by what proportion would you be willing to reduce Y0 to bring the value of the economy back to the old level? And that's the maximum you would be willing to sacrifice in order to bring about the good outcomes. And the formula for that is very easy to calculate. So theta is the compensating variation as a proportion of GDP. And you can work out very similar formulas in the multi-region case. We take, for numerical value, 4 regions: China, US, Europe, and the rest of the world. And you'll notice that deliberately I put China first, as is going to be the case very soon. And we take data on fractions of the world GDP, fractions of emissions, et cetera, from standard sources, which are cited in the paper. So just to give you an example of the kind of exercise that we do, the baseline parameter values, we take the discount rate at 5%. And this, again, is something very far from what the real hawks on need for climate change policies like Nick Stern would ask, closer to the discount rates that Marty Weitzman and company would. we take the growth rate at 3% and the rate of increase of emissions under status quo policies also at 3%. That can be debated. The carbon dynamics values I cited earlier. The parameters of the stochastic process for catastrophes are chosen so that the probability that there is no catastrophe at all will fall to 10% in 80 years. And we got this basically by asking people, do you think this is reasonable, or is that reasonable? And this is basically the sense we got. Again, I'm perfectly open to other suggestions. The miracle technology process, we've got such that the probability that the whole problem disappears will rise to 50% in 70 years. Initial GDP equal to 1 is just a normalization, and the initial value of catastrophe is twice GDP. That I got by looking at the estimates of the costs of Katrina in terms of actual capital destroyed, both physical levees, et cetera, and personal homes, et cetera, human lives lost, all that added up. This looks very reasonable. Thanks. The thing we look at for policies is, most interestingly, a Kyoto-type reduction of the rate of increase of emissions from 3% to 2.1%. If the whole world does this, it should be willing to pay 3.3% of GDP, quite a high number. But if the US dropped out, the willingness of the rest of the regions to pay drops to 2.1%. And that's the sense in which I said that the policies are strategic complements. The willingness to pay increases if the others are also paying. If others are reducing their emissions at the Kyoto rate that we stipulate, the US would be willing to pay, for selfish reasons, only 0.6% of GDP. It would free ride and get the benefit of the others' reductions. And if no others are actually undertaking the reductions, the US willingness to pay is only 0.4% of GDP. Again, the strategic complements idea comes through, and maybe this is behind the US idea. The others are being very nice in Paris, so let's drop out and get the free riding benefit. Fairly simple other things like what happens if discounting is at a lower rate, then the compensating variation rises. If the probability of tech solution increases, what would we be willing to pay for that? And that's fairly similar, 3.3% of GDP. It's not exactly the same, but it's similar. So these are the quick preliminary results that we've got. Again, to emphasize, the model is kept very deliberately simple. You can request the Excel file and do your own experimentation, but the concrete results suggest that quite substantial investment is justified. All of this dealing with just catastrophes. You can add on to the model other types of uncertainty. For example, normal uncertainty you can add on by making the GDP Y a decreasing function of X and things like that. So if the world were being rational and cooperative, I would be fairly optimistic. Maybe that's the miracle you're looking for. But my pessimism is exactly about the national and international cooperation that's required, especially in view of strategic complementarity that we are finding. And so I think that should really be a major focus of future research. Maybe I should have gone before Scott, because then I would say this should be the focus of future research. And he would say, no, that's fine, I've already done it, and this is what we find. So thank you very much.